Hey everybody, and welcome back to Patel Academy. Today I wanted to finish up the topic of sequences and series by talking about power and Taylor series. In terms of what I specifically wanted to talk about, I wanted to start off by introducing the idea of a power series, as well as talking about some key terminology associated with it that we haven't seen in previous videos. Furthermore, I wanted to touch on the applications of power series, specifically on modeling functions to make questions significantly easier. Then I wanted to talk about Taylor series, and Taylor series are a special kind of power series that we'll look at with some special properties regarding specific functions such as e to the x or sine x or cos x. And then I wanted to end off by talking about the Lagrange error bound, which pertains to the Taylor series. So let's get right into it. What exactly is a power series? Well, traditionally in the series that we've looked at in the past, we've only involved the variable n. So we've had expressions such as the sum from n is equal to 0 to infinity of 1 over n, for example, the harmonic series. Power series are special in the fact that it involves not only the index n, but it also involves the variable x. And this is extremely useful because it allows us to model functions of the form f at x with series. So the general form that I'll write to the side over here is of a power series is the sum from n is equal to 0 to infinity of some constant c at n, and then times x minus a to the power of n. Now, what exactly are the key things associated with this? Because this isn't like a series that we've seen in the past. So the key things to keep in mind regarding the series are the radius and the interval of convergence. And I'll explain more about those. So what exactly is the radius? Well, the radius of convergence, denoted by r, is some number such that this expression x minus a has to be less than the r for the series to converge and has to be greater than r for the series to diverge. And so remember that because in previous series with our tests, including the ratio test and the root test, we've always involved absolute value, suggesting that the series can converge as long as the expression is the absolute value less than 1, for example, or greater than 1. In this case also the absolute value applies. So we have if x minus a is less than r, there's convergence. And if x minus a is greater than r, there's divergence. So that is the radius r. And then pertaining to that is the interval of convergence, I. So what's the interval? Well, the interval essentially measures, based on this value of r, what values can x take on such that the original series can converge. And so by looking at this inequality, you can probably solve it such that x has to be less than the quantity a plus r, and x has to be greater than the quantity a minus r, if you consider the inequality formed by the absolute value. And so this is considered the interval of convergence. So how exactly do we find these two things? Well, the two main tests that we'll be using are the ratio test and the root test. So ratio test or root test. Now why these? Well, if you remember, based on the parameters of the ratio and the root test, the value that we get at the end, that limit value L, has to be either less than 1 for convergence or greater than 1 for divergence. And if it is equal to 1, then the test remains inconclusive, but for most of the power series that we'll encounter, you'll either get a less than 1 or a greater than 1 definitive answer. And so the ratio test and the root test really allow you to set up this inequality and find the radius of convergence very easily, because you essentially have an expression has to be less than 1 to converge. And so you just solve for whatever your x value is going to be in this inequality to get both the radius and the interval. Now, one of the key things to keep in mind is that regardless of the radius, because the radius can take on any number of quantities, infinity or even 0, it's important to know, and I'll put this by asterisks, that the series will always converge at the point x is equal to a. So I'll just write that over here. Series will converge at x is equal to a. And so why is that important? Because when you're solving for the radius or the interval, right? Let's say if you're using the ratio test, then you get some limit as n approaches infinity of some expression of n. I'm going to call this g at n. And then because you have terms regarding x inside this absolute value, you can actually bring them out. So in front of this limit, you'll get the multiplication of some function f at x. And so there's three main cases over here. The first case is that this limit as n approaches infinity, I'm going to call it L. The limit is equal to a constant that's not 0. And so what happens then? Then all you have to do is just solve the inequality. So you can just find r. And with r, you can also find I. Now the second one is if L is equal to 0. So if this limit as n approaches infinity of this function g at n is equal to 0, then that means that this entire limit will always be 0, regardless of what x values you take on. And so what exactly does that mean? Well, that means that because the limit is always 0, it'll always converge by the ratio test. And because of that, x can take on any value. And so it logically follows that the radius of convergence, has to be infinity. And then I has to be negative infinity is less than x, which is less than infinity. And you can use interval notation if you want. Over here, you would use or negative x has to lie between negative infinity and infinity. And keep in mind, I use round brackets over here to suggest that infinity is not included as it's not a number. The idea of round brackets versus square brackets is going to be very important. The third scenario that can occur is when L is equal to infinity. And so if this limit as n approaches infinity of g at n, the absolute value of g at n is infinity, then that does not necessarily mean that the entire series will always diverge. Because there's a point f at x, for the function f at x, there's a point x such that that's 0. And 0 times infinity does not necessarily imply divergence. In fact, you'll find that the point 0 at which that function f at x is 0 is going to be the point A. And that ties into our original idea of that the series will always converge at x equals a regardless of what this limit turns out to be. And so in this case, the radius will be 0, and our interval will just be a, or the point x equals a. And we do still call it an interval even though it is just a point for convention's sake, but for this special case, there is only one point such that the series will converge. And then one important thing to consider is that when you are finding the interval, I, it's important to check the endpoints always. Because our inequality, when we're solving for L, suggests that L has to be less than 1. However, because the point L is equal to 1 in the ratio test is inconclusive, we have to test that back into our series. We have to plug that point back into our series and then identify using some of our series convergence tests whether that resultant series will diverge or converge. And from that, we can figure out if these boundaries are less than or just less than and equal to. And so it's essential that you check the endpoints and then you use a convergence test. And so oftentimes these will be things such as the geometric test, maybe it'll be a p-series, something of this sort. So this video, I wanted to heavily focus on examples of going through the things, not only to solidify the idea of power series and then in the future Taylor series, but also to give a quick review of the ratio and the root test, which are some of the more important tests that you need to know in terms of convergence. It'll be a recap from last video. So for this first example, we have this series as n goes from 1 to infinity of 6 to the power of n over n times, this is where the power series comes in, 4x minus 1 to the power of n minus 1. And so in this case, remember, there's only two options that we can use, the ratio test or the root test. So in this case, I'm going to use the ratio test. So remember, the ratio test is the limit as n goes to infinity of the absolute value of this function, this inner part, evaluated at n plus 1. So I have 6 to the n plus 1 over n plus 1 times, in the numerator, 4x minus 1 to the n. Keep in mind, this is because there's n minus 1 in the numerator, so when I add 1, it becomes n. And then times this original. So it's times the reciprocal, sorry, of this. So it will be n on the top, and then divided by 6 to the n times 4x minus 1 to the n minus 1, all in absolute value. And so, just doing some simplification, well, we see that this 4x minus 1 to the n and this 4x minus 1 to the n minus 1 stuff will cancel, and we'll be left with a 4x minus 1 on the top. So I'm going to write that. So remember to keep your limit notation the entire time. So limit as n approaches infinity of the absolute value of 4x minus 1 times this 6 to the power of n plus 1 over 6 to the power of n. That will cancel to leave just a 6 on the top, and then times also this n on the top, and then divided by n plus 1. And that's the cancellation. And then recall that because we have the variable x inside this expression where we're taking the limit with respect to n, we can pull that out, and we can also pull a constant out. So this actually becomes 6 times the absolute value. Now this is essential. Remember that even though we're pulling it out, the absolute value still has to stay attached to the expression 4x minus 1. So it's 6 times the absolute value of 4x minus 1, and then this is times the limit as n approaches infinity of the absolute value of n over n plus 1. And we can evaluate that specific limit to be equal to 1. And so by the ratio test, we have this expression, which is our final limit, 6 times 4x minus 1, and the absolute value must be less than 1 for the series to converge. And now this is a key thing to remember, is that when we are solving for the radius, we can't actually leave it as the term 4x minus 1. We have to factor out a 4 because the coefficient in front of the coefficient in front of the x has to be a 1. And so we get equals 24 times the absolute value of x minus 1/4 has to be less than 1. And then we get the familiar expression of x minus 1/4 has to be less than 1 over 24. And so this expression follows our idea of x minus a, the absolute value, has to be less than some value r for the series to converge. And so we can safely say from over here that our r is equal to 1 over 24. Now what about I? So then all we have to do is set up the inequality. So we have the absolute value of x minus 1/4 has to be less than 1 over 24. So considering the absolute value, we have negative 1 over 24 has to be less than x minus 1/4, which has to be less than positive 1 over 24. And so we get our interval as being 5/6 has to be less than x, which has to be less than 7/6. And so you might think that we're done, but if you recall, what I said on the previous slide was that we still have to test the endpoints. And so we have, so when we're testing our endpoints, we first test the lower bound of x is equal to 5/6, and when you plug that into the original series, you get the series as n goes from 1 to infinity of 6 to the n over n times negative 1/6 to the power of n minus 1. And so this, I can tell you, is equivalent to the series of 6 times negative 1 to the power of n minus 1 over n. And so, based on this information, now over here I did remove the n equals 1 and infinity from it, but it's implied. I just took it out because for this specific case it's not necessary to know those bounds. This is an alternating harmonic series. If you use the alternating test, you can find out that this actually will converge. Even though it'll conditionally converge, it will indeed converge. We call it convergence. And so we know that at this endpoint, x, the value of x, where it's 5/6, will allow the series to converge. On the other hand, when you have x equal to 7/6, I'm going to skip this first step of plugging it in, and I'm going to tell you that this final series is going to just be 6 over n. This is a normal harmonic series, and we know that it diverges. And so our interval becomes 5/6 has to be less than or equal to, because of this convergence at the endpoint that we tested, x, which has to be less than 7/6. So that's an example of the power series and all the steps you'd go through if there are no special cases. These next two examples, I wanted to illustrate what actually happens with one of those special cases. So if we have the sum as n goes from 0 to infinity of n plus 1 over 2n plus 1 factorial times x minus 2 to the power of n. Once again, I'm going to use the ratio test. So I'm going to get the limit as n approaches infinity of the absolute value of n plus 2 over 2n plus 3 factorial times x minus 2 to the n plus 1, and then all multiplied by the reciprocal of this, which is 2n plus 1 factorial over n plus 1 x minus 2 to the power of n. And so what do we get over here? Well, when we simplify this, we get the limit as n approaches infinity of the absolute value of, I see that I keep this n plus 2, this x minus 2 to the power of n plus 1 on the top, and then x minus 2 to the power of n on the bottom will cancel, so I get just an x minus 2 on the top. And then over, if you keep in mind that 2n plus 1 factorial divided by 2n plus 3 factorial, well, we can split up that bottom factorial into 2n plus 3 times 2n plus 2 times 2n plus 1 all factorial because of the definition of the factorial. So on the bottom, we just get those two factors, so it's 2n plus 3 times 2n plus 2, and then this n plus 1 in the second term, we can't forget about that. So we have this expression. And so we don't have any constants in this case, but we do have this x minus 2 component that we can pull out, and then this is times the limit as n approaches infinity of this function that I'm going to write quickly. Alright, and so what do we notice? Well, on the top of this expression that we're taking the limit of, it's a first degree polynomial, and the bottom would be a third degree polynomial. So as we take the limit as n goes to infinity, we'll get 0 for that value. And so if you remember, because this is 0, our radius becomes infinity, and so our interval is equal to negative infinity is less than x, which is less than infinity. And in this case, of course, there's no need to test the endpoints because it's infinity, so it's not a number that we can necessarily test for. There's no need to test for it. So a very quick answer to this is simply just using the ratio test, identifying that the limit is 0, so regardless of the x values, this must converge because 0 is less than 1, and so our radius of convergence is infinity. So this third example, this final example, is going to be how we use the root test, and it's also going to be one of those special scenarios. And as you can probably guess, it's the scenario when the limit is equal to infinity. So using the root test, we take the limit as n approaches infinity of this original function, so times 2x plus 17 to the power of n, and then we raise that to 1 over n. And then just recall as a note, the limit as n approaches infinity of the quantity n to the power of 1 over n is equal to 1. And this will play a role over here. So this becomes the limit as n approaches infinity of the absolute value of n squared. So it's n to the power of 2 plus 1 over n over 4 cubed times 2x plus 17. This is just me distributing the 1 over n. And so doing a little bit of algebra in one step, I bring out this 2x plus 17, and then I have the limit as n approaches infinity of, I have the quantity n squared times the quantity n to the power of 1 over n over the quantity 64. Now I could pull the 64 out, but as you will be able to tell, it won't matter. The limit of this second term, this n to the power of 1 over n, is just 1, but this n squared, when you plug in infinity, it's infinity, i.e. the limit does not exist. And so what happens is that this limit L does not exist unless this quantity 2x plus 17 is equal to 0. Now it should be an absolute value, but 0, when you're setting the equation equal to 0, the absolute value doesn't matter, especially because it's a linear term. If it was a quadratic term, it would, but because it's a linear term, it doesn't matter. And so we get our x value is equal to negative 17 over 2. And so because the series will converge at all points other than, will diverge at all points other than this, and this makes sense because if you consider the x minus a term, if you make the coefficient of x 1, then you get x plus 17 over 2, so it's x minus negative 17 over 2, so this is the a value. We get our radius is equal to 0, and our interval is just x is equal to negative 17 over 2. And there we go. So those are 3 examples of how exactly you can test for the interval of convergence and the radius of convergence of the power series. Moving on to the next topic, I wanted to talk about how we can model functions using the power series. Now with just a power series, it's a little bit harder to do so for complex functions, but for the geometric series function, or for functions based on the idea of the geometric series, this is a wonderful tool to have. So let's recall that if we have the quantity 1 over 1 minus x, right? We established in the previous video that the geometric series converges to the quantity a over 1 minus r. And so if we use that, we can rewrite this working backwards as the series, in this case, of x to the power of n, because our a value is 1, our r value is x. And so why is this useful? Well, first of all, it's important to notice that this is only true if the absolute value of x is less than 1. In the geometric series test, it's the absolute value of r is less than 1, and in this case, r is x. Now, one of the important properties before we delve further into this is the idea that in terms of convergence of something pertaining to x, let's say we have a series x to the power of n plus 1, right? The convergence or divergence, in this case, of this series is the same as if we were to pull an x term out of the series completely. So we can have x times the series of x to the power of n. This is a really important tool because oftentimes when we're trying to model functions as a geometric series, we're going to need to start shifting x terms from the outside into the series. And it's important to notice that the convergence doesn't change at all because of these operations that you're doing. Same thing you can probably guess with moving a constant out from outside of the series into the series. It won't change the convergence at all. So this is an important property to know. In terms of other ideas of modeling functions, so we'll work through some examples of how exactly we can use this idea of converting a function as a series in terms of the geometric series. There's also the idea of differentiating and integrating. So differentiating, well, what happens if you have a series and you want to differentiate it, or maybe you have a differential equation that you want to model as a series, because that is a thing that will come up in the future. Maybe not specifically on the AP exam, but something like integrating a series may come up. And so you essentially have to use just your derivative rules on solely the x component. So let's say if I have some value f at x is equal to the series x to the n. Then I'll just do a few derivatives just to give you the basic idea. So also important, the notation for derivatives after you get past like the second or third derivative is you raise f to the exponent of your derivative. So if it's the fourth derivative, for example, then I'd raise it to the exponent of 4 and I'll put that 4 in brackets. That suggests the fourth derivative. So in this case, the first derivative of f, now you could use prime, but after a while there would be too many primes, so that's why this is like the shorthand notation. So the first derivative of f at x is equal to the series of n times x to the n minus 1. Makes sense. However, an important thing to notice is, let's say if I started from n is equal to 0 to infinity. This new series, there's actually a shift. And it goes to n is equal to 1 to infinity. So each time you take the derivative, you increase your starting value of the series by 1. So if I do the second derivative, you use the same rule, but remember this time now we're going to go n is equal to 2 to infinity of n times n minus 1 times x to the power of n minus 2. And so while I'm not going to put the general formula on here, you can fairly identify that this n times n minus 1 will model some sort of factorial in the general form. And you'll also get, it's basically you're just using your power rule of the derivative on the component that has an x. The same thing would apply if you had x minus a, for example. So some term x minus a to the power of n when differentiated would become n times x minus a to the power of n minus 1. And recall that while chain rule will apply in this case as well, 90% of the power series that we'll get will have a 1 in front of the x, so chain rule won't even matter. But keep in mind that if you do have a series with a 2, for example, in front of the x, then you do have to multiply the series by 2 because of chain rule. In terms of integration, a similar rule applies. You simply use your integration power rule on the x or the x minus a components, but in this case there is no shift in index because your series isn't going to start at n is equal to -1, for example, or n is equal to -2, depending on how far you go. You stay at n is equal to 0, and also remember that the integration constant c will need to be put in front. So let's say if I have, once again, f at x is equal to from n is equal to 0, the sum from n is equal to 0 to infinity of x to the n. Well, the integral of f at x with respect to x, so f at x dx, is equal to, I always like to put the c in front, just because it makes it easier rather than making it a part of the series itself. So I do c plus the series, we stay at n is equal to 0 to infinity of, using this power rule, we add 1 to the exponent and divide by the new exponent, so I get x to the n plus 1 over n plus 1. And so these are the basic ideas of how you can use power series to model functions, and the idea of integration will come up potentially in Taylor series applications as well later on in the video. So working through an example, the idea behind this question is to try and transform it into a power series. So how are we going to do that? Well, given f at x, I'm going to rewrite this by bringing the 3x squared term in front of the fraction. Why? Because our general term of the geometric sequence has to follow the idea of 1 over 1 minus some value in terms of x. And so what I'll get is I'll get 3x squared. I'm going to do 2 steps at once. I'm going to move this 3x squared in front, and I'm also going to factor out a 5 from the denominator. So I get the 1 minus something term. So I get 3x squared over 5 times 1 minus 2 over 5 times the cube root of x. Right, this is just using algebra. There's nothing that's changed about the function or its value. This is just algebra in order to get it to our desired form. And so now what can we say? Well, remember that I told you that if an x value, or if a term regarding x is inside or outside of the series, it doesn't affect its convergence as long as it's not related to n. So I can actually write 3x squared over 5 and then times the series, in this case it's as n goes from 0 to infinity, of, now in this case we have our a value is 1, our r value in this case is 2/5 times the cube root of x, and this is to the power of n. And now, while you could leave it like this, this isn't necessarily the cleanest form, so we can bring these x terms and this 1 over 5 constant inside the actual function, and then that'll help clear things up and make everything inside the summation. And so what we end up getting is that this is equal to the sum as n goes from 0 to infinity of 2/5 to the power of n times 3/5 times x to the power of 1/3 n plus 2. This is just algebra. So the 2 to the 5 to the power of n I took out from this value within the series. I multiplied the 3/5 in, and then I had the cube root of x to the power of n, which is the same thing as x to the power of 1/3 n, or n over 3, and then I added 2 because I'm also multiplying by this x squared term on the outside. So I get that series. So this is our final power series. But as we've done in the previous examples, with any power series, it's essential to know the radius and the interval of convergence. And so we look back to our value r and we say that, okay, well, the absolute value of r, or in this case, the absolute value of 2/5 times the cube root of x has to be less than 1. And so using the absolute value properties, we get x to the power of 1/3, the absolute value, has to be less than 5 over 2. So x has to be less than 125 over 8, the absolute value. And so this becomes our r. And then in this case, our interval would be negative 125 over 8. Has to be less than x. It has to be less than positive 125 over 8. And in this case, specifically, when you're using geometric series, you don't have to test for the endpoints because it's a strict requirement that it has to be less than, and the endpoints where r is equal to 1, where the absolute value of r is equal to 1, will never converge. In the ratio or root test, it was inconclusive, which is why we had to test for the endpoints, but for the geometric series, it's a strict no on the endpoints. So moving on to the next example. In this one, I'll do the same thing as the last example where I'll find the power series, but I'll also do an additional component by taking the integral just to show you guys an example of that. So same as the last one, I have h at x. I'm going to rewrite this as x to the fourth over 9 times this 1 over 1. Now in this case we have a plus, but that's okay. That's an easy fix. So I have 1 plus 1/9 x squared. But what exactly is that equal to? Well, it's x to the fourth over 9 times 1 over 1 minus the negative version 1 over 9 x squared. And so putting that into our power series, we get x to the fourth over 9 times a series that then goes from 0 to infinity of negative 1/9, negative 1/9 x squared all raised to n. And so doing some simplification on this, we end up getting that the series becomes the sum as n goes from 0 to infinity of, I always like to pull out this negative 1 term outside just by convention of the alternating series. So I get negative 1 to the power of n times 1/9 to the power of n plus 1, and then all multiplied by x to the power of 2n plus 4. Now you might be wondering how I got this 1/9 to the power of n plus 1. Well, by taking out the 1/9 to the power of n, you also have to remember that there's a 1/9 outside of the series that I brought in. So I get 1/9 to the power of n plus 1. Now I have x squared to the power of n, so that's x to the power of 2n, and then add 4 from this x to the fourth outside of the series. And so this now is our final power series. Alright, now taking the integral. Now the integral of h at x dx. You could solve this without using the series interpretation. Depending on how comfortable you are with integrating, it might be easier to do so, but it does involve some techniques that aren't commonly covered. Like it involves, first of all, you can do it two ways. You can use trigonometric substitution, but it's quite a lot of steps and involves multiple different techniques. Or you could use polynomial long division and then use your inverse trig formulas in order to identify the final integral. But sometimes it might be easier, instead of identifying and making all those connections, if you've already converted it into series form, it might be easier to just integrate the series rather than going back and integrating the original function with all of those. So I'm not going to bother writing in h at x over here, but know that when you're taking the integral, you get, I'll write the c in front first. So it's c plus the sum, again there's no shift on this, so it's the sum from 0 to infinity of, we still have negative 1 to the n, and then we still have 1/9 to the n plus 1, but now in this case we're going to have x to the 2n plus 5, and then all over 2n plus 5. So that would be the integral and the answer to the original question. Alright, now let's talk about the final major topic, and then associated with this will be the absolute final topic, the idea of Taylor series. So what exactly is a Taylor series? Well, it's just a type of power series. So if you're comfortable with the idea of a power series, then Taylor series shouldn't be that bad. It's just sometimes a little bit harder because there's an added component in the idea that there's derivatives involved in it. And so the general formula of a Taylor series is that f at x, so this could be any function, is equal to the sum from n is equal to 0 to infinity, generally, but it can be n is equal to 1. That is still allowed, and you'll see in one of the examples of the application of a Taylor series that we will be using n is equal to 1. So we get from n is equal to 0 to infinity of the nth derivative at the point A divided by n factorial times x minus a to the power of n. And the terminology we use, the reason why there's a's involved in multiple places here, because we call this a Taylor series that's centered around or about the point x is equal to a. And so this will become important in the next thing that I'm going to talk about in the next slide, which is the Maclaurin series, which is a special type of Taylor series centered around the point x is equal to 0. And setting a is equal to 0 is probably the most common Taylor series that you'll find. However, Taylor series can exist at other points A. And so what exactly does this Taylor series represent? Well, it's just a way to model a function, essentially. So it's the series representation of a function. And so while I'll talk about the specific application of the Taylor series in the example that I'll do, we can essentially consider the Taylor series as a way to approximate the values of a function, but over larger intervals than something like the tangent line approximation, which is meant to approximate a function at a specific point, or a point very close to a known point. And so you may have seen this graph before, but the idea is that the Taylor series, so if we have a cosine graph, the Taylor series, as n goes larger and larger, will very closely model this graph. So we might see like our first Taylor series being something like this, and then our second Taylor series may be something like this, and then our third Taylor series may be something like this. And then the idea is that as you get closer and closer to infinity, you will be able to approximate better. Just label these for anyone who sees this graphic later on in the video. So the general idea of a Taylor series is just a series representation of a function. The important thing is Maclaurin series. Now, what exactly is a Maclaurin series? Well, as I said earlier, it's just a Taylor series about the point x equals 0. And so, while this may not be very much more complicated, because the general form is still quite similar, it's the sum from 0 to infinity of the nth derivative at 0 this time over n factorial times x to the n. It's a little bit simpler. There are some important functions that we have that have very defined Maclaurin series, very simple Maclaurin series, and I'll show them in a minute. The other idea that I wanted to introduce here was the idea of remainder in series. Now, we have seen in the last video the idea of the alternating series remainder and how we can use that to approximate a function with the partial sums. In this case, similar to partial sums, we have the idea of the nth Taylor sum. So it's the nth Taylor sum. And so this will tie into the last topic that I'll talk about, which is the Lagrange error bound. But it's essentially similar to when we're approximating series, the normal series. We have a remainder, Rn, which is equal to the actual value of the function, f at x, minus the nth Taylor sum. We have the absolute values. And so why is this important? Well, the idea is that as n approaches infinity, we want a remainder to approach 0. However, there are specific instances where we want to approximate our Taylor series, or we want to approximate our function where we can only use the nth Taylor sum, and we can't actually identify it across infinity. So it's the idea that while the limit of r at n approaches 0, there is an error function that we can use to approximate r at n, which is a little bit more helpful than this idea of just the function minus the nth sum, because we don't exactly know the function value, always. And so before I move on to some practice problems and cover the error, I wanted to just make a note of the important Taylor series, and I will do this in light blue. So the first one is e to the x. Well, e to the x can be defined in terms of its Taylor series as, sorry, I'm going to redo that sum sign. As the sum from n is equal to 0 to infinity of x to the n over n factorial. As you can see, this is a lot simpler from what the original Maclaurin function was, where it's the derivative constantly. But why does this make sense? Well, the derivative of e to the x is just e to the x, right? And so each consecutive derivative is just going to be e to the x, but because we're evaluating it at 0, e to the power of 0 is just 1. So each time, that numerator is just 1. And so we just get, in the end, x to the nth over n factorial. And so our first couple of terms, so when n is equal to 0, we just have 1. And then plus when n is equal to 1, we have x plus x squared over 2 plus x cubed over 6, dot, dot, dot. And so this is an important one to know, because a lot of times our functions will be related to e to the x, and so it's important to know how you transform these series with regards to e to the x. But knowing this baseline series will help a lot. The other ones were cosine of x. This is another very important one, not only just for the AP exam, but even later on in your math careers when you learn about series and differential equations. In terms of series, these Maclaurin series will come in a lot of help. So it's from n is equal to 0 to infinity of negative 1 to the n. So this one is an alternating series times x to the power of 2n over 2n factorial. And so what is this, essentially? Well, when n is equal to 0, our numerator is just going to be 1. Our denominator is just going to be 0 factorial, so 1. So we still get this 1. But now we have minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, dot, dot, dot. Now related to this is sine x. It's, although not the same, it's very similar. It's negative 1 to the power of n still times x to the power of 2n plus 1 over 2n plus 1 factorial. And so we get similar, we have a 1 on the top, because when it's, when n is equal to 0, we have x at the start, and then minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and then we continue. The other important ones, now one of them that does come up, not as often on the AP exam, but in first year university, this one is really important, it almost always comes up, is ln of 1 plus x. Now, unfortunately, ln of just x is much harder to come up with a Taylor series for, but ln of 1 plus x, surprisingly, is quite simple. And so this becomes the series as n goes from 0 to infinity again of negative 1 to the power of n plus 1 times x to the power of n over n. And then the last one, which also can come up, again, not usually on the AP exam, but in first year university it does come up, is the inverse tangent of x, which is kind of odd considering it's not a very common function compared to these other ones, although ln of 1 plus x isn't as common either, but ln x is. This one is, again, an alternating series, so it's negative 1 to the power of n times x to the power of 2n plus 1 over 2n plus 1. And so if I wanted you guys to remember the important ones, I'd say that e to the x, cos x, and sin x are the most important. And then if you want ln of 1 plus x, the inverse tangent of x isn't like that much important. Alright, so now we get into the practice of Taylor series. So these problems are all about they're just asking us to come up with a Taylor series. And so for this first one, x to the 6th times e to the power of 2x cubed about x is equal to 0. Well, we just looked at what the Taylor series for e to the x is, right? We know that e to the x is equal to the sum. Now keep in mind that this is the Maclaurin series, so that's why I can use the substitution, because this e to the x series that I'm going to write is about x is equal to 0. So what I can do is where I see an x, I'll just plug in 2x cubed because it's centered around the same point. So e to the x is equal to the sum from n is equal to 0 to infinity of x to the n over n factorial. And so I can use e to the 2x cubed is equal to the sum. Now in this case I'm not going to change it. I'm not going to write n is equal to 0 to infinity because it's constant. In the next example you'll see that I might do a little bit of, not the next example, but the example after that, the last example, I'll do a little bit of shuffling around with the index just to make it work in terms of the restrictions on the function. But in this case, in terms of x to the n, now it becomes 2x cubed to the power of n over n factorial. And so when we consider multiplying by x to the 6th, remember that if the x to the 6th is outside of the series, we can just bring it in, so it's fine. So we get x to the 6th times e to the 2x cubed is equal to the sum of 2 to the n over n factorial times x to the 3n plus 6. And so that is our final Taylor series. I'm not going to bother doing the convergence or the radius or the interval of convergence of this, but you can use the same tests in order to figure out how exactly this converges. Now for the second one, this one's going to require a little bit more work because now it's not centered around x is equal to 0. And even if it was, we don't really have the Taylor expansion for 1 over x. So this will require a little bit more work. And so for examples like this, you have to go through and write out the derivatives. So my f prime at x is going to be, and a helpful tip that I tell you guys is do not actually multiply out when you're writing this, otherwise it's going to be almost impossible to see the patterns. So for this first one, keep in mind that this function is just 7 times x to the negative 4th. So you can just take the derivative using the power rule. So I get negative 7 times 4 times x to the negative 5. Oops. And this is when n is equal to 1. Now f double prime of x is equal to positive 7, 4 times 5, x to the negative 6th. This is when n is equal to 2. Now the third derivative, in this case it would be negative. And so you guys can probably see the first pattern already, that it's an alternating series because we're going negative, positive, negative, positive. So 4, 5, 5, 6, x to the negative 7, in this case n is equal to 3. And I could keep going, but what's important to know in this case is that there's a 7 that's constant, I see my power of x, when you factor out a negative, it's constantly increasing by 1. It's also 4 more than the n value each time. So I see that as a pattern. I see it's alternating, so I know there's going to be a negative 1 to the power of n in this case, because the odd terms are all negative, the even terms are all positive. And then I also see that there's this 4, then the 4 times 5, then the 4 times 5 times 6. Later on, there'll be 4 times 5 times 6 times 7, and then times 8. That resembles closely a factorial. But the problem is that we don't have exactly the 2 times 3 term in front. So what I could do is I could write negative 7 times 2 times 3. So I'm going to multiply it by this value, 2 times 3, and then I'm just going to divide it. So we still maintain equality, except now what you find is that I actually have 6 factorial on the top, right? And so what happens is that we can beautifully simplify this expression into its general term in terms of n. And so what do we get? Well, we get that we have a constant 7 over 6 times this alternating negative 1 to the power of n times, now keep in mind when n is equal to 1 it's 4 factorial, n is equal to 2 it's 5, n is equal to 3 it's 6, so we have an n plus 3 factorial, and then times x to the power of negative n plus 4. Right, and so this will simplify into 7 times n plus 3 factorial over, now we'll get we'll still have this negative 1 to the end, and then we'll have over 6 times x to the power of n plus 4. But remember that when we're finding the Taylor series about a point, we have to plug in that point for x. So my f at n at negative 3 will become 7 times n plus 3 factorial over, now because I'm plugging in negative 3, I can actually take out a negative 1, so this will become 6 times negative 1 to the power of n plus 4 times 3 to the power of n plus 4 with this negative 1 to the n, and then because they cancel out, so the negative 1 to the n will cancel out, I'll be left with negative 1 to the power of 4, which is 1. And then I'm actually going to distribute this, I'm going to break the 6 up into its components 2 times 3. So I'm going to get, in the end, 7 times n plus 3 factorial over 2 times 3 to the power of n plus 5. So once again, the negative 1 terms canceled out completely, and the resultant was just 1. Then the value 6 I broke up into 2 times 3, and I put the 3 into the power. So because I'm adding 1, it goes from n plus 4 to n plus 5. So now that I have my general term, I can plug it into the formula for the Taylor series. This is a formula that you should memorize. So I get the series from n is equal to 0 to infinity of 7 times n plus 3 factorial over 2 times 3 to the power of n plus 5. And then this is all over n factorial. So this is the nth derivative formula divided by n factorial, and then times x minus a to the nth. So in this case, substituting again, a is equal to negative 3, and then simplifying with the factorials, I get the final Taylor series as being the sum of 7 times n plus 3 times n plus 2 times n plus 1. It's going to be hard to fit. Over 2 times 3 to the power of n plus 5. And then times x plus 3 to the n. Barely managed to fit it. And so that's how you would find the Taylor series about a point that's not equal to 0, or if you have the point 0 but you don't have any of those key functions that you can just use a transformation on. So that's an example of just finding the Taylor series. And here's like the challenge question of today's video. It's identifying the Taylor series for an integral. Now you might be thinking, well, we haven't learned at all how to do anything even remotely close to that. But the trick is that we know how to integrate a series. And depending on the conditions, of course, but for this specific example, it is true that the series of an integral is the integral of the series. You can do a swap between the integral and the series. And why is that useful? It's because we can just find the series expression, the Taylor series expression of this inner integrand, e to the x minus 1 all over x, and then we can just take the integral of that with respect to x to find our final Taylor series expression. And keep in mind, this is about x is equal to 0, so it's Maclaurin series, and I see an e to the x, and that's good news. So once again, I'll restate that e to the x is the sum. Now in this particular example, now this isn't really intuitive, so on something like the AP test, I'd specifically advise to always keep this index of summation written out each time, so n is equal to 0 to infinity. But for this specific case, it's really important because I will do a slight index shift at the start and at the end. So I get e to the x is equal to the sum from n is equal to 0 to infinity of x to the nth over n factorial. But now in this case, I see that in the numerator I'm subtracting 1. What I also notice is that when n is equal to 0, the first term, as we saw in the expansion of e to the x, it's 1. So why is that useful? Well, I can rewrite this as 1 plus the sum as n goes from 1 to infinity of x to the n over n factorial. Why does this work? Well, it's just because I took the 0th term out, so now I'm just taking the series from n is equal to 1 to infinity, and 1 is that very first term. And so I can get e to the x minus 1 is equal to the sum from n is equal to 1 to infinity of x to the n over n factorial. Because I'm subtracting 1 from this whole series, the plus 1 at the start cancels out, so I just get the original series, but this time the index starts from 1 and goes to infinity. Now why is this useful? Well, now we can just multiply this by 1 over x. And so remember that 1 over x, if we're dividing by x, we're just subtracting 1 from the larger power, from the numerator, sorry. So we get x to the n minus 1 over n factorial. Now why is this useful? Well, if you notice in the original, x is equal to 0, there's a restriction. You can't divide by 0. But in the series expansion, it allows us to actually have x is equal to 0 as a term. Now, of course, in this series itself, n is equal to 0 is not like a term within the series expansion, but x can be 0, and that's important here. And converting back to the n is equal to 0 is really easy once you use the index shift. And so what are we going to do? Now we want to integrate this. So the integral of e to the x, sorry, the minus 1 is not in the power. So e to the x minus 1 over x dx is equal to the integral. This time the series is short, so I can rewrite it, of x to the n minus 1 over n factorial, n is equal to 0 to infinity with respect to x, which is equal to, once again we have our c plus our sum from n is equal to 0 still, or sorry, this is from n is equal to 1. Now remember in this case that unlike the derivative, the index doesn't actually shift. And so we get c plus n is equal to 1 to infinity of x to the n over n times n factorial. I add 1 to the top power, so it becomes x to the n, and then divide by the exponent, so it's n. And now if I wanted to convert this back into the n is equal to 0 index, so from n is equal to 0 to infinity, we'll think about it. If I wanted to subtract 1 from that index, I'd have to add 1 to each occurrence of n in the actual series. Or if you think about it in terms of index shift, right, I can let I equal n minus 1. So when n is equal to 1, the I value is 0. And then because I is equal to n minus 1, n is equal to I minus 1. I can write this down on the side. So I'm going to let I is equal to n minus 1. So if n is equal to 1, I is 0. And then I plus 1 is equal to n. So wherever you see n in the original expression, you just add 1. And this becomes the series from n is equal to 0 to infinity of x to the n plus 1 over n plus 1 times n plus 1 factorial. And you see a function, the integral of a function, something that looked really hard to do. In fact, actually that integral isn't possible with elementary functions. You can't use any technique to actually integrate that. But now with the help of series, we've come up with a valid answer for what the integral is, and that too about a point where the function itself doesn't exist. So the Taylor series is centered around a point where the function doesn't exist, but because it's a Taylor series and there's no divided by x in the denominator, we can come up with a proper expression for this integral. And then the final topic I wanted to cover was Lagrange error bound, however you want to pronounce it. And so essentially, going back to the idea of the remainder that I was talking about, this is a way to get an accurate representation of what the remainder is, and thus the error of your Taylor series approximation at any given point. And so we define, I call it LEB. So we say that the absolute value of the remainder must be less than or equal to, and this is also a formula that you probably should memorize. It's equal to the n plus 1th derivative evaluated at some value c over n plus 1 factorial. The top part is absolute valued, but the n plus 1 factorial, n is going to be greater than 0. So that factorial value is going to be greater than 0, so it doesn't necessarily need an absolute value. And then times the absolute value of x minus a to the power of n plus 1. Now you might be wondering, what exactly is this c value? So we recognize what a is. A is equal to center. And we know what n is. N is the term exactly that we're using to get the error at that point. But what exactly is the c value? Well, technically, c can be any point between x and a. It's a point between x and a. However, to maximize the accuracy of your error bound, or to find out the best level of accuracy, which is often what the AP exam will ask you, they'll have a question that's like, prove that the error of the Taylor function at n is equal to 15 is less than or equal to 0.005, or less than or equal to 1 over 3021, for example, a very specific value. And to get that very specific value, it should be a point at which the function is maximized. Or at least it should be, it should be where that derivative is maximized. However, oftentimes that derivative may not be a function that can be easily maximized. For example, if you have, let's say, because on the AP calculus exam there are questions that don't allow for calculators. So if it's like a quartic function, for example, the easiest way is to either take c as the point A, or to take c as the midpoint between x and a. And so what that'll allow you to do is it'll allow you to get a rough estimation of that maximum value of this derivative, and allow you to get a very highly accurate error value. And so in terms of what we covered today over the video, We talked about power series and we did some examples of not only how to identify the convergence and the interval of convergence of power series, we talked about how you represent functions closely related to the geometric function using power series. And then we talked about Taylor series, and we talked about its application in terms of identifying the Taylor series for an integral, for example. And then finally, we talked about the Maclaurin series, and we talked about the Lagrange error bound. Thank you so much for watching, everybody. Please remember to like and comment down below if you want to see more or any specific type of content, math, physics, chemistry. Big thank you to the Brampton Boys for your support to the channel. Remember to subscribe and hit that notification bell to see when I drop my next video. Once again, thank you all so much for watching, and I'll see you guys next time.